So far, we've discussed how networks might grow in ways that differ from the Erdős-Rényi random graph. What I'd like to talk about next is how growth, specifically in networks, can lead to some of the skewed degree distributions that we see in real-world networks. Here's an example of one such network. It's the Java Forum, an online question and answer forum that my collaborators and I explored to see if we could automatically identify experts. It turned out that identifying the experts was super simple. All we had to do was look for people who had replied to lots of others, and these indeed ended up being the most expert users as evaluated by humans who are actually reading their replies. Here I've also colored the nodes by whether they have an edge to another person because they replied to their question or because they posted a question and received the reply. So the repliers are colored in red and the askers are colored in blue. We can look at the degree distribution and see that it's highly skewed. It's more skewed in the case of the repliers because you see that some repliers have replied to upwards of 1,000 other users, but it's rare for an individual to have received replies from more than a couple of dozen different helpers. In this case, the distribution that I've plotted is the cumulative degree distribution. And this means that we're not looking at the probability that you had interacted with exactly k other people, but k or fewer other people. In any case, we do see some deviation from a straight line, but overall, especially for the repliers, we see a very high skew. This isn't the only instance of seeing a very highly skewed degree distribution. Another example is the network of human sexual contacts. And even though men do tend to report having had more partners than women do, in both cases the degree distribution for both men and women is highly skewed. And this has interesting implications, for example, for the spread of sexually transmitted diseases. Now, in a little while, like next week, we'll focus more on identifying the true power laws from the fakes. But for now, let's just assume that we're seeing a true power law distribution. The way that we're going to recognize it is that we're going to have a straight line on a log-log plot. Now, if we had plotted the same power law distribution on a linear scale, we would hardly even see it. We would see this very sharp drop off, basically like an L shape, and we wouldn't be able to tell whether a node had any chance of having degree 40 when most other nodes have degree 1. But if we look at the log-log scale, we can see that even though it's not very likely, just a fraction of a percent, that someone would have degree 40, it's not negligible. And in fact, this is what is called a heavy tail. That is, the probability drops, but it doesn't drop exponentially. It doesn't do this. Instead, it keeps going decade after decade. We can contrast this with the Poisson distribution, which, if you remember, this is the distribution that describes the degrees in an Erdős-Rényi random graph. Here I've even been generous and I made the average degree be 10. And now we might ask the same question: what is the probability that someone has degree 40? Well, on the linear scale, it looks 0, like it did for the power law distribution. But if we now plot on a log-log scale and we look around 40, we see that that probability is actually very small, something like 10 to the minus 10, and by the time you're over 50, right, this is 10 to the minus 64, so this is actually 100. There's no chance that someone would have degree 100, no matter how large the network is, if it's an Erdős-Rényi random graph with an average degree of 10. So there's a very stark contrast between the Poisson distribution of the Erdős-Rényi and the power law distribution that we see in many real-world networks. So let's look at this power law distribution. What we saw essentially was a line on a log-log plot, which means that the log of the probability of having degree k is equal to some constant minus alpha, this is our power law exponent, times the log of the degree k. And so if we exponentiate both sides, we get the probability of having degree k is equal to another constant times the degree k to the minus alpha. So let's check if we understand what's going on. As the exponent alpha increases, so this, we're not talking about minus alpha, we're talking about the exponent alpha, the downward slope of the line on a log-log plot, what does it do? Does it stay the same, become milder? So from your point of view, does it do this? Or does it become steeper? Does it do this? Given that many real-world networks seem to display power law degree distributions, what we'd like to do is come up with a network model that can produce these distributions as well. And for this, we're going to need two ingredients. The first of which is that the network grows over time. So as time goes on, you have more and more nodes added to the network and more edges. There are many networks for which this seems plausible. For example, if you look at citation networks, when a new paper is written, it will cite papers that have come before it. Although social networks are not power law, and this is not so much that people don't want to connect to very popular people, but practically speaking, we can't keep up in a meaningful way with thousands or tens of thousands of friends. So even though social networks are not power law, you can imagine a similar dynamic where individuals join the network over time, whether through birth or another process that they land in a given social network, and then they're going to start forming edges to other individuals within that network. There's going to be a second component, which is that when you come into the network, you're going to have some edges that are allocated. For example, if you're a new paper, you're going to have, say, 30 or 100 or who knows how many citations that you're going to give to the papers that have come before you. So in the social network context, what you're deciding between, or I guess let's stick to the papers. So in the papers context, what you're deciding between is citing a paper that no one else has cited or citing a paper that lots of other people have cited. In the social network context, you might be deciding between connecting to someone who doesn't have many, if any other connections, or connecting to someone who's popular and has lots of social ties. And if you prefer the person who has lots of social ties, in fact, if you prefer him or her in proportion to the number of ties that they have, then this is called preferential attachment or cumulative advantage. Let's first look at the first factor, which is that the network is growing. So here I've used NetLogo to grow a network where each new node comes in with two edges that it allocates. So you can see that some nodes have more edges than others, but it's still relatively evenly distributed. The edges are between the nodes. We can derive some properties of the degree distribution here, and in order to do this, we're just going to look at what's going on. And what's going on is that at each time step, you have one new node coming in with m edges to allocate, which means that at time step t, you're going to have t nodes. Now let's look at a node that's born at time I, and we'll call its degree k sub I. We know that k sub I on average is going to be changing at a rate of m over t. Why m over t? Well, at each time step a new node comes in and it has m edges to give, but it's going to allocate them among the t nodes that are already there. So each individual node is competing with those t others for the m edges. We can then see what happens, over the lifetime of that node, since time I when it was born to time t, how many edges do we expect that it has? So we integrate the change in its degree from I to t, and we add the m edges that it had up front. And this is just the k sub I t is equal to m plus m log t over I. From this, we can see that on average, nodes that were born earlier are going to have more edges than nodes that are born later. They've simply been around longer and have been accumulating and accumulating these edges. What I'd like you to think about is in which ways this is realistic or not. So if you think about social networks, what other modifications to the model might you make in order to make it more realistic? Okay, back to our very simple model though, with no modifications. We just have nodes arriving over time. Now we want to derive the degree distribution. And for this, we're going to be using the fact that nodes that are born later are going to have lower degree on average. So for example, if we want to know what is the probability that a node has degree 100 or less, we're going to figure out at what time a node with average degree 100 was born. We'll call that time tau, and then the fraction of nodes that have lower degree are just going to be the ones who are born after it. So this is t minus tau over t is that fraction. And we have the solution for the degree of a node that was born at time tau from before. So we're just going to solve for tau from this equation and derive an exponential distribution for the degree of the nodes. So given that this is an exponential distribution, what I'd like you to answer is, what do you expect this degree distribution to look like on a log-log plot? Is it going to be a curved line or is it going to be a straight line? The second ingredient we need is that of preferential attachment. That is, when the new nodes come in, they're not going to just connect to any node at random. They're going to prefer some over others, and in fact the ones that they're going to prefer are the ones that already have a lot of edges. This kind of process is also known as a cumulative advantage process, a rich get richer phenomenon, or the Matthew effect. That is, those nodes who already have a lot of edges are going to get even more disproportionately. In fact, it's going to be proportional to the number of edges that they already have. The first such model proposed for networks was proposed by Price for citation networks. In his model, you have papers coming in, and each paper is going to cite m other papers on average. But instead of just citing any old paper it can find, it's going to cite other papers in proportion to the number of citations the paper already receives plus 1. That plus 1 is a little trick to make the model work, because a lot of papers start out with no citations at all. So if you were citing in proportion to the number of citations, you'd have a cold start problem. So this kind of helps the process along. The process generates a very nice degree distribution, which has a power law exponent with alpha equal to 2 plus 1 over m. A lot of the real-world citation networks do have power law exponents slightly above 2. So it's just a very nice match and a very nice description of reality, where a few papers get lots and lots of citations, thousands, tens of thousands. But most papers are relatively neglected. They get no citations at all or just a couple. You might think, well, preferential attachment makes sense for social networks. If this little node is coming in and he's saying, well, who's going to be a good friend to have? Well, the person who has no friends, well, they can't introduce me to anyone else. Maybe they're not such a good friend to have, but this person here, oh, they're so popular, let me connect to them. Now, how does this translate to papers? Why would you want to cite papers that are already well cited? Well, you know, for one, they're probably better, but there's also a lot of anecdotal evidence that it's a little bit of a luck of the draw, right? You can have two scientists making pretty much the same discovery, but one paper gets a lot of attention and the other one is relatively unknown. So how can this happen? Well, one way in which it happens is through a copying mechanism. So when I'm reading a paper that I think is relevant to my research, I'm going to look at the references and the papers that it cites, and then I might copy one of those references after I read it, of course, right? I might copy that into my my own paper. And if you think about it, the chance that I encounter a citation to a paper is proportional to the number of papers who cite it. Now, there could be other mechanisms. For example, the better cited a paper is, the more likely it is that the authors are invited to give talks, which in turn means that more people find out about the paper, etc., etc. So that's one possible preferential attachment mechanism. Now, what really set off a lot of research in complex networks was the model proposed by Barabási and Albert, which is similar to the Price model, but not quite. And what they were aiming to do was to describe why there's a power law distribution in the number of inlinks that different web pages receive. So in their model, you have new web pages arriving over time, and they're each going to link with m links on average to web pages that are already there. And the probability of linking to an existing page is going to be proportional to the number of other pages that are already linked to that page. And so this probability here that a given new node is going to connect to node I is going to be equal to m, which is the number of new links it has to add, the degree of node I over the sum of the degrees of all the other nodes. And this results in a power law exponent of 3, which is a little bit problematic because the web degree distributions are much closer to 2, and 3 is a relatively steep power law exponent, meaning that you don't get the most popular websites would not be as popular as you would see in the real world. So but you can correct for this in various ways, and Barabási and Albert did indeed do this later by introducing different fitness for different sites, meaning that some sites are just a little bit more interesting, and so they get more links. But let's see how this model works. So if we were to simulate it, we would start, say, with a connected component of 3 nodes who all link to each other, and now we're going to add new nodes one by one, but we want to keep track of the degree of each node, and so for each edge we're going to record the endpoints and enter them into a flat list. And then when a new node comes in, so say 4 comes in, it's going to choose from this list of 1, 1, 2, 2, 3, 3. But now if it happens to choose 3, now 3 has degree 3 and is represented 3 times. And so now when 5 comes in, it's a little bit more likely that it's going to choose 3 as well over 1 or 2. Or actually over 1, which only has degree 1 still. So that's the basic mechanism, and I've implemented it in NetLogo as well, so you'll get to play with that. After a while in NetLogo, what you see is a network such as this one, where hopefully when you compare it with the purely random growth model, you're seeing bigger hubs emerging relative to here. With the random growth, you have the older nodes are accumulating more links, but not nearly in kind of a skewed fashion as is happening in the preferential attachment model. We can also examine this analytically, as Barabási and Albert did. So again, we're just looking at how the degree of a node I changes over time, and we've already specified this. So at each time step there are m new links going around, and they're going to be allocated in proportion to the degree of the node divided by the sum of the degrees, and here it's just t times m edges, and you have 2 endpoints for each edge, so it's just t times m times 2. And what we'll see again is that if we want to figure out what the probability is that a node has degree, say, k prime or less, what we want to figure out is at what time point tau was the node with average degree k prime born, and then we know that everyone born after that will on average have had lower degree. And so following a similar derivation, we have this distribution that says the probability that a node has degree k is 2m squared over k to the third. So this is your power law exponent of 3. So besides this nice power law distribution, other properties of this network, which this one actually holds for the growth model as well, is that it's just a single connected component. And this is simply due to the mechanism, which is that we're adding a node at a time, and it's linking to the nodes that are already there, who link to the nodes that are already there, and so everything ends up being connected. If you remember, we also looked at a growth model where new nodes were being added, but the new edges were not necessarily coming from the new node. And in that case, of course, you don't necessarily get everyone in the same component. So for some graphs, it might make sense. So for example, for web pages, you might assume that maybe the links are only added when the web page is created and they're not added after the fact. But for other networks, it might make more sense, if you have a social network, maybe initially a person who's come to a new city doesn't know anyone, but they get to know someone and then they get to know more people. So it really depends, right? For citation networks, this seems to be a very appropriate model. And the final observation, which is also consistent with the random growth model, is that again you have the older nodes having more edges, and the newer nodes, the youngins, actually don't really have a chance to catch up because they're born much later, and so they're born with when they're born, they have very few edges. The older nodes have been around longer, and some of them have gotten really big, so they're going to continue to accumulate. So if we look at these two nodes, this one was born at time equals 5, and this one's born at time equals 95. And so you can see that they're both kind of tracking in terms of their growth, and since this is a log scale, really at the point that the older node has over 100 edges, this younger node just has a few dozen, right? And it's not really catching up. So you'll have the opportunity to try this yourself. So let me see if I can switch to the model. Not this one. This one, not this one. Okay, please be this one. Okay, great. So sorry about that. So here in this model, you can use preferential attachments. So let me do that. So hopefully you'll observe lots of hubs here. Now if we have the probability of preferential attachment be 0, and you can use anything in between as well. So we're going to set this up, and so it might seem similar at first, but the thing to do is to look at the degree distribution and also look at the size of the nodes to see if you can spot the difference in the two networks. Again, they're both growing, but one has preferential attachment and the other one does not. So just to test your understanding, relative to the random growth model, the degree distribution in the preferential attachment model is going to resemble a power law distribution less or more. So just to summarize the growth models, the reason for doing growth models is that most networks aren't born, they're made. They grow over time, and this means that some nodes, the older nodes, might accumulate more than others, but if you have this additional ingredient of preferential attachment, then nodes that for whatever reason end up with more edges as the network grows are going to accumulate even more edges at the expense of other less fortunate nodes. Now, for the assignment this week, what you'll be doing is looking at the implications of these models for diffusion. And so even if you're mostly just listening to the lectures, I think that, doing this assignment will be, it'll be a cinch, and it'll be interactive. In the sense that you'll be playing with these NetLogo apps. So I encourage you to do it even if you don't turn in the assignment. I think it'll be worthwhile. So the one part of it will be looking at, and let's see if this is the case. Oh, nope. It'll be looking at the Erdős-Rényi random graph, and here you'll be looking at what does it mean to have a giant component that doesn't occupy the whole network for how disease is going to spread. So you're going to have one node infected, and then that one node is going to start infecting others, and then those nodes are going to infect others in turn, and you'll see what happens. And in another part, you'll be looking at how quickly information or disease or other things can spread on the network depending on whether the network grows randomly or grows with preferential attachment. So hopefully it's this one. Okay, great. So you'll be setting up your network, and here it's not preferential attachment, and then you're going to start spreading, and you're going to see how long it takes for the information or disease or whatever to spread. So I hope that'll be fun, and this is the end of week 2. Thanks.